Welcome, everyone, to this webinar titled Drilling Geothermal Wells, Learnings from Oil and Gas and the Path Forward. This series is brought to you by the GEODE consortium, which is led by Project Interspace and the Society of Petroleum Engineers and funded by the U.S. Department of Energy's Geothermal Technologies Office. My name is Haley, and I'm your facilitator. Please note we are recording this call and we muted all lines. Today's event will last up to 90 minutes. We encourage you to ask questions throughout. Simply click on the Q&A button at the bottom of the screen. It's now my pleasure to welcome our moderator, Ahmed Amir. Ahmed is currently a global fluids advisor at Oxy. His career spans over 19 years, during which he has held operational, technical, and R&D roles in fluids, digital solutions, and pressure control equipment domains at two major service companies. At industry events, Ahmed has participated as a steering committee member, session chair, reviewer, panelist, and presenter. He has served as an advisor to graduate university programs, holds intellectual property, and has authored over 30 publications, including classes for SPE regional chapters. Ahmed is a member of API Subcommittee 13, chairman of the 2022 AADE Fluids Conference and AADE Fluids Management Group, as well as an advisor to AADE's Houston Chapter Board. He was selected as an SPE Distinguished Lecturer for the 2020-2021 tour and was previously recognized as one of the 40 under 40 recipients. He holds a BSc from Cairo University and is currently pursuing EMBA and MSSE degrees. I'll turn it over to you now, Ahmed. Thank you.
Thank you, Haley. I'd like to start by thanking the GEODE consortium for their support to develop this web event. Now pleased to announce our speaker, Mr. Hani Ibrahim. Hani is a well construction SME with Blade Energy and Mazama Energy on SHR EGS wells. He's previously held operations director with XGS Energy, well construction manager with HMP Technologies, drilling advisor, area drilling manager for DNM and Schlumberger. His career traverses across many engineering and operations, global positions with operators and service companies with global coverage. And he's an SPE member for over 40 years. He's also a member of AADE, GRC, and IADD. He has taught many oil and gas industry seminars and published many SPE papers, mainly in the area of drilling optimization. His involvement in the drilling optimization effort has been for over 20 years for multi-million drilling optimization projects. In the drilling industry, for 40 years, he has worked in EGS, AGS, ACHR, and new technology development for the geothermal industry. And he holds a Bachelor of Science in Petroleum Engineering from the Suez Canal University. Hani, you may begin.
Thank you, Ahmed. Pleasure to be here with you guys. And I'll also start with thanking SPE and GEODE for getting me to present this webinar. So the webinar, as Haley said, it's really trying to leverage our knowledge in oil and gas and get that knowledge to the geothermal wells to make it more profitable and get the ball rolling on that. We see a lot of innovations and a lot of initiatives happening in the past couple of years, and would like to capture that and be on the top of that. But when we start, let me start with a little small question here. We have a problem-solving questionnaire for you, and I'd like to see how many people will get it right. This is from a Mind Tool page, as put it there, and 6 plus 4 equals 210, 9 plus 2 equals 711, and 8 plus 5 equals 313, and 5 plus 2 equals 37. What is, in your opinion, 7 plus 6 would be? I'll give you a minute to look at that. Okay, have you thought about it? If you got 113. That's the right answer. And the idea is to subtract the first two digits here and come up with this digit, and then add the other two and come back with it. What I'm trying to do with this is try to open your minds about different ways of looking at things and different concepts you might be overlooking if you look only within your domain, if you like. So let's start with a little bit of a background on the geothermal energy. Geothermal energy, as most of you know, was kind of a marriage in a sense to the ring of fire, which is basically around all the continents and caused by the plates movement and volcanoes around that area. So we have a few volcanoes and a few rifts here between the continents, and that's where most of the hydrothermal wells originally started. So you can find out all of them in a web map, of course, but it's basically that's what it is. Now, a group of people they come up with this heat depth contour map, which is considered a new kind of a concept for drilling the geothermal wells. Because we have, as we will discuss later on, we have new types called EGS and AGS and super hot rock and hot dry rock in there. So they came up with this, kind of a map, heat map, saying that you can get the 450 degrees C, which in a sense, we'll talk about this later also, why we're targeting that kind of a temperature. This is about above 900 degrees Fahrenheit. We can reach that temperature, in places marked red here. So you can see a few of them, here, closer again to the volcanoes. 5 to 7 kilometers, orange is a little bit more, pronounced. And then at 7 to 9 kilometers, you find almost west of the United States, west of Latin America, east of Latin America a little bit, the Middle East, Europe, Saudi from all places, and other places in India and Japan and Singapore. So what are you saying here is that we can reach that kind of a temperature right now, but we don't have to reach the 450 degree. We can reach less than that in less depth than this. And this is 5 to 7 kilometers, which is about 15,000 to 20,000 feet. So let's go back to the concept of well construction. What do you need from well construction? Well construction is a complicated, and I'd like to, give kind of a kudos to my friend John Dwart, who started this kind of drilling is a system of systems because it's everything is related to that system, and we need to look at everything we have. So we collect the data, and we have the formation. Then we study the data, QC it, analyze it, come up with the permit, of course, for the area, do the risk analysis meanwhile, and then look at for any issues about drilling you might see and how to mitigate them if you have new solutions. Then we select the rig, we prepare the FE, we prepare the drilling depth versus days. And then we select the service companies and we allow that. Look into logistics and procurement, order our casing, our wellheads, and stuff like that. Then we turn around and look at the location and say, okay, let's set up the location, and then we'll start drilling the well. So it's not an easy task and it takes time, but before we start everything, we need to have the data. Data is important, and then we have also the geology is important to us to know where you are. You'll be surprised to see the similarities between oil and gas industry and the geothermal. So both using drilling rigs, both drill string, bits, casing, etc., etc. So you find a lot of similarities, and as a proof of that, you see that Utah Forge, which is really a great, kind of a testing ground to a lot of new technologies in geothermal, are using a regular rig, regular pipes, top drive, everything is the same. Having said that, there is some dissimilarities or, kind of difficulties to run with that. The drilling rig, most of the drilling rigs right now are catered in the States, are catered to the shale, unconventional. So they're reducing the size of the rig and reducing the number of the rig as well. But the capacity to run large casing deeper is one of the important part of the geothermal wells, because as you will know later here in the discussion, we need a larger casing to produce more heat, and as such, you need to run that larger casing deeper. So imagine if you run 958 casing, for instance, to about 15,000 feet. That's a lot of weight to carry by the mast, as well as the casing itself. It would be like a 5,350 pound per foot, which means a lot more than the regular capacity we have right now of 750 or so pounds. I think it relates to about 1.2 million pounds to carry. The dressing itself need a lot of it of looking at as well, because it's going to be deeper as we look into the token drag. It's going to be exposed to high temperature for longer time. There is possibility of having H2S, there's possibility of having CO2, and these are basically causing corrosion and embrittlement to the steel. Then drill bits, we will see we're going to go for roller cones or PDC bits live and see how that goes. There is the casing, of course, saying about the corrosion. There is a design for the casing, separate design. The corrosion is a factor, as we mentioned, for H2S and the CO2, and the production from the hydrothermal wells, all the geothermal, if they go through certain rocks. The most important part, though, is the thermal cycling of the casing between the operation phases. For instance, you cooling the well while cementing, and then you have the heat coming up with a hot fluid from the next section drill. That cycling is bad, but also there's a cycling through the production, and you have to have the casing suited to handle that. Drilling fluids is another very important component here. What you're looking at is a fluid that can withstand all these high temperatures. And when I say high temperatures, everything is there above 200 degrees, kind of get all the mud systems out of the question, because no gels or no kind of additives can withstand higher temperatures like that. So this is some kind of a dilemma we have right now. And you can see that most of the drilling fluid used in geothermal drilling right now is basically water, kind of a brine or water. Another problem, kind of a more in the area of the hydrothermal wells, is the losses. You see a lot of losses and loss circulation, complete loss circulation, and there's a lot of people like to either to go through this and cement the casing, of course, so they have to have a solution for that. Cement, again, very important part of this of the well construction. Really, they have to have temperature resistant cement or high temperature resistant cement, should I say. And the recipe varies from one vendor to another, but there is a few, kind of a ways to capture the temperature. But again, to capture the temperature, high temperature, and cope with it. But again, you have to be careful because again, everything kind of comes down to high temperature and what type of well you're drilling. Formation evaluation, No tools in the market right now is rated above 350 Fahrenheit, for drilling and basically for formation evaluation as well. Some cases we have 500-degree Fahrenheit, tools, but again, they're limited in use and you have to be used in certain ways and cooling the well. Rental, you have a lot of rental tools off the shelf for oil and gas and easy to get as well. But the rental tools for geothermal wells are really scarce, if you like, and you can't find them everywhere, and you cannot really get them to the right place in the right time, which brings us to the logistics. Again, most of these geothermal wells right now are in kind of a odd places close to volcanoes or close to areas where there's no oil and gas activities there. So gets up to a little bit into a problem for the logistics. And then supervision, you see a lot of people are not aware of the geothermal wells and what kind of HSE things that they have in there. So you have to be aware of what they have in there. So the consideration for well construction, basically, as it was behind, but the five main factors here that you're drilling in high temperatures. Sometimes you have high pressure and compressive strength for the formation. There's corrosive, liquids around, maybe crystalline rock, which is what we're mainly going to concentrate our efforts on, because basically you have a granite or metamorphic rock in there, and it's hard to drill over UCS about probably 50,000 pounds or so or above. And then we have fractures that included into the scheme of the drilling the well. So we have some learnings from the oil field which we can apply. Again, I'm repeating my friends John here was saying is a complicated system of systems. We need to have a holistic approach to this, to any problem in the oil field, and the same thing for geothermal. Basically, we cannot think individually about what I can perform or what I can provide to the system or to the drilling well construction of a well if it's not affecting other people. Everything is affecting something else. So it's a domino effect, if you like, or a Jenga, again, if you like. The reliability of the system really, especially for EGS system, or we're going to talk about a little bit more here, is dependent on consistent measurements. And measurements have been a little bit of kind of a miss and go in the oil business as well. So we don't have an accurate, really accurate measurements for the depth. We cannot really say where we have at the moment. So it's all dependent on the rig and the measurements and the steel measurements, if you know that. And basically, we don't have a sensor. In the end, the sensor itself is going to be affected by the temperature, so we need to be careful about that. There is kind of a pride, if you like, which I like a lot about our industry, drilling industry. But everybody turned to his own affiliates, if you like. So drilling contractors really follow the IDC. Drilling engineers follow SPE in most cases. API standards are not regularly updated. And then the surface companies and operators don't have really any kind of a existing body to control or have their own standards. So everybody has its own standards, if you like. So the geothermal wells, of course, as we mentioned before, we have the environment and inherent limitations to the standard oil and gas. Most of the oil and gas temperature operating maximum is about 150 Celsius, or about 300 degree Fahrenheit. Anything above that is a special and or kind of a specially provided. We have some tools running up to 175 Celsius or about 340 or so Fahrenheit. However, there again, if you're looking at the EGS system and the AGS system, we're going much higher temperature than this. So we need to be, kind of worried about the shortened exposure time, or we're going to have some damage for sure for these tools. So going back into again oil field learning, we know that the drilling and completion time here. I'm not going to read all that, but you have a drilling almost like a quarter of the time, less than a quarter of the time of the whole scenario here. We have a lot more time spent in flat operation and then in completion and other things than the actual drilling. However, everybody's looking at improving the drilling time here. This is the low hanging fruit, if you like. There is a lot of efforts going through shortening the flat time, and we'll talk about this in a minute. Connection time and running casing and stuff like that. But the emphasis is really so far has been cutting the drilling time lower and lower. But we have some kind of problems when we have, the tools provided in the oil and gas fields are kind of concentrating on the oil and gas solutions and the environment they run in. And as such, we don't have exposure over to the geothermal world. We have, again, the sequence in oil and gas, we're looking into the G&G guys are talking in centuries and eras and stuff like that. Production, looking at maybe 20 years of production line. Drilling people want to have things in per day. I think we found out that if we don't really have a holistic approach to have the tools working with everything else, going back to the system of systems and what's effect on everybody else, that is really essential and crucial in the success of drilling the geothermal wells, and whatever learning we got from oil field still can valid into the oil field as well. So we have some conceptions and for the transition to the future. We need to have a little bit of state of risk, higher state of risk because of the temperature. Temperature is our frenemy, as I like to call it. It's our friend and it's our enemy in the same time. At a certain level, you cannot run tools, you cannot run things you want to run in a well because you're limited to the temperature, envelope of that tool. However, the higher the temperature, as you can see later on here, the higher the temperature is the better, return on your investment here. So we'd like to operate into a higher temperature environment. Planning is really important because you need to know exactly where you're going for the tools. Identify the performance from the past wells, bring in some new equipment or adapt some of the equipment existing to try to work it in that kind of an extreme environment. The kind of expensive if you really follow some of the practices that you have in the past without really thinking about the heat and or the component of the well, which is basically the rock, very hard rock to drill. I think we need to have a lot of brain power, have input on the mitigation of all the problems that we might have. Again, the damage is happening because of few things, because of temperature to start with, formation strengths and abrasiveness of the granite and basalt. directional planning to go into kind of a demanding operation, while you cannot achieve that build rate or turn rate in the formation you're thinking about. And the wellbore stability, because that's an important part, is some of these geothermal wells have kind of components in there turn to break and freighter on you. So I think just following again the oil and gas, the DWOP or drilling well on paper is a very good kind of a practice to bring everybody together, all the stakeholders, to really look at things from their own perspective and share that with everybody on the same time. There is a critical path on what we need right now, because sometimes you need this information, or you need this tool right away to kind of improve the performance, but also show that the performance is replicated and can be dependable in creating future wells. But also in the meantime, we would like to have the geothermal industry attractive to the financial world, so they can invest more and more into the geothermal and reach a level of investment like the oil and gas have or enjoy, should I say. So looking back at the oil and gas as well, we have oil rigs here. This is from 2000 to the year 2015. You look at the number of rigs here. It's kind of below the 500 level until you reach the 08, and then started higher and higher to about 1,500 rigs in 2015 or 14, and then started to drop again. Was that a bad thing or a good thing? We'll see what we have here in a minute. But I think we have the all the involvement and innovation from the service companies and from the rigs contractor, that we have more robust tools. I'm sorry, more robust tools that drill further and faster. We have rig automation. Connection time is shortened, handling how to handle going back after connection after trips. Maintenance is automated on the rigs now, so that minimizes really the MPT for rig repairs and all that stuff. We have a lot more remedies for correction the well problems. We have directional control in the rigs now, and automation and remote sensors and everything. So that helps us a lot. And basically what we see here, I gather this data from the rigs. So you can see this is the rigs, the wells per rig. And you can see even with a slowdown in the rig count, you see the number of wells per rig are increasing. So the rigs are drilling well. Then the footage per day and the lateral footage in particular are increasing in general as the studies go. That tells us a few things here. That tells us basically we have better tools. We drill more kind of a factory-like wells, if you like, and you get that into a standard optimization system. So you improve and you carry on with improving every time you do the rig, you do the well. But I'm trying to offer you something new here a little bit. We had the Stone Age invented the wheel. This luggage carrier invented in the 18th century. It took about 19 centuries to come up with, kind of a carrying suit or, bag on wheels. And everybody's using that now, and nobody thinks about it. It's been invented, 350 years before BC, and this invented in the 18th century. How come nobody thought about this? This is what we call a recombination. I think it's a great idea to have that into our thinking and our thinking. Another example is the press and getting the Gutenberg press. It's basically took some time. It's a very long time ago, and then basically we had this mold comprised of holding the letters that led to the printing press of Gutenberg, which now is a kind of, if you look at it, nobody look at that at all as something weird or different, but it's all recombination. So what I'm preaching here is basically trying to get everybody to use another idea from another field or another world, and then combine it with what we have here to come up with a good solution for geothermal wells. So, as I said, we have few geothermal wells types, if you like. The older types were in the, as an example, in the geyser here in West USA. Basically, there are what we call hydrothermal wells. So you drill the well and to an aquifer, and that aquifer, once you reach that aquifer, you set a liner, slotted liner in most of the cases, and produce from that. And it depends on the quantity of water that is still into, or steam, still in that aquifer. And typically they have higher temperature, 400 degrees Celsius or so. So it's a really good, kind of a investment and power generation. However, again, it depends on the size of the water aquifer, how much we have in there. And they've been trying to improve that quality if the wells drop down or the water content drop down by drilling some wells here and injecting water into these. So there comes that injection water here. And basically what you get the heat out and you turn a turbine, and that will give you the traditional or conventional geothermal system. When you talk about enhanced geothermal systems, which is a whole different category we're talking about right now, is that we have duplet wells or more wells drilled into the hot area, granite rock, and then we have an injection well drilled in a separate well and get injection or water in there, and by passing the water through a path between the two wells, you get a hot water back up again, and then you can generate the power from that. Several types of this EGS. We're not going to go a lot of more into that, but there's either hot dry rock, which is basically drilled to a rock that does not have any passage through or any fractures or any water reservoir in there, and you inject the water, and that water will carry through there. The other type is to go to SHR, which is super hot rock, and you drill really deeper down, as we mentioned, to reach the 450 Celsius target, and that again you pump the water from one well and receive it from the other well, and that will be your system. Some variation of that from people. They're innovating and trying to connect the pipes or connect the well bores together. And some people will call it closed loop. And some other things that they say we'll combine the production and injection well in one. And we have what we call a monobore or closed system geothermal. And that will give you a single bore well that you inject the water from outside the casing inside the production casing, and receive that or retrieve the heat out via some kind of a insulated tubing in the middle. So having said that, we have kind of categorized the geothermal applications. As we said, is the hydrothermal, which is a traditional conventional way it used to be in the past. the direct fuse, which is basically in Europe more than here. We have a lot of space heating and kind of working with that. Japan as well have a lot of hot spas and stuff like that, which is they really like and keep. These are the last three ones here are really new types. So we're talking about the hot dry rock enhanced engineering geothermal, what we call as EGS. So basically, as I said, pumping in a subsurface fracture system, and without having the aquifer in there, and you heat the water by contact to the water to the rock, and then pump it back to the surface. The AGS, as I said, use uh, excuse me, use the single monobore to basically pump water outside the tubing and retrieve the heat inside the insulated tubing. And then we're looking at really the top part here is the supercritical hot rock, which we call SHR, and the temperature in these above 375 or 700 degree Fahrenheit. So why we're going for the high temperature? We're going for the high temperature because basically, whenever you see this curve here, these are the production per well. And once you see the LCOE is basically levelized cost of electricity or energy, it's dropping down fast by the amount of production from the well. So if you produce well, about 13 megawatts, that will give you some kind of a about less than $13 per megawatt production, which is again that's where the profit comes from. The IDDP project in Iceland reached actually about 25, and the production was high, it's about 35 or 36, megawatt per well. So the amount of production coming from that is a better way to produce and to get return on your money. There's also when you look at the LCE versus the temperature, as you can see here on the bottom, these are the temperature in Celsius, and the higher temperature, give you a higher return on your money, so you don't have the LCOE as high as 100% for 170 degree. And right now, I think the most of the wells drilled is about 210 Celsius EGS. So you're looking at 75%, kind of a cost for the LCOE. However, if you reach above the 375, as we said, you're looking at 15% or less. So that's why we're going for the hotter rock or the deeper wells. Now, this is a little bit full slide. I don't want to, kind of read it all, but I'm trying to show you the different types of the geothermal wells here. So there's a hydrothermal we talked about, and the EGS natural, and then the EGS enhanced, which is kind of pushing the water from outside and trying to fracture as well, stimulated fractures. This EGS natural would be kind of a limited natural fractures included already in the rock, existing in the rock, as I said. And this is basically the hot areas where you have a hot aquifer. The closed loop, collect heat from HDR, heavy, hot, dry rock, or super hot rock. So, looking at looking at the rock EGS, you're looking at creating that kind of a fracture network down there. That fracture network can be really, much as natural fractures, or kind of stimulated fractures. And The idea here is again to pump up cold water or a working fluid. Some people are using supercritical CO2 to do that, and pumping through this open fracture system. And that open fracture system will gain the heat from the rock and then go back up after it's getting heated to the second well or production well, and then basically have your power plant on the top here today. Some of the concept or involve the stimulation of the rock, which is basically means the hydraulic fracturing. And as such, we have seismic monitoring existing on most of the wells here, just to try to see what kind of a seismic events may happen while you're stimulating the well. So again, this is a busy slide. I'm not going to read it. Just trying to really get everything we need to really become as successful as the oil and gas in our efforts for geothermals. And the requirements, and as you see here, is database offsets and the geology information, seismic information, reservoir information. The drilling itself has a lot of things that we need, specifically the bits, the MWD, LWD, the rotary steerables, the PDMs, the mud, and the LCM material. And since this is a drilling thing, so I'm going to concentrate a little bit about the drilling aspect of this. But there is a lot more here because we have, the power plant itself costs money. Transporting the oil, the heat is really non-existent as a time being, because we cannot transfer the heat via pipelines or anything available for the oil and gas at the moment. And that's create a lot of problems. So that means that you have to have the power plant close to the wells, and that's another area of exploring we need to do to come up with a better plan for it. So we have some development, some people who are trying to work on on developing new ideas and concepts, and I'm gonna share some with you. But before we do that, we look at the geothermal focus really. We're all talking about this thin crust on the top of the earth. We're not really going that deep. Some wells have gone as deep as I think this is one is the longest I can find out. It's about 12 kilometers. There's a Kula super deep. It's basically I think it was in Federation, Russian Federation, and the KTB in Germany. It's about 9 kilometers, and these are deep as possible. But in order to reach really deep and get that heat from the liquid core, whatever it comes up. You're looking at the wells here drilling, trying to drill close to any magma, kind of interrupting the mantle and going into the crust and becoming earlier, closer to the crust, which basically means closer to a volcano to get that. So you're looking at wells drilled conventional here. Super hot rock is basically trying to read there, but in order to get the really, really deep super hot rock anywhere, as per the map we just saw, we need to have tools and things to go beyond that. One of them is the drill bits, of course. Everything is hanging on a drill bit, since it's the first thing that meets the rock, or rubber meet the road, if you like. So we're looking at some people did a lot of more on the cutter types and the cutter shapes, and having work with that a lot. That way we can increase the weight on bit to drill through the granite and the high formations, high compressive strength formations we encounter while drilling in the oil and gas. So that is important for us, but also what's important is the torque stability because we have a lot more vibration while drilling hard rock, of course. The temperature, because that's while you're drilling, you're generating a lot of temperature at the localized contact between the cutters and the rock, but also you have a hot temperature coming from the rock itself, so we have to compensate for that, and you have to cool the well and cool the bit, and especially to get a higher penetration rate and get things. Some of the concept as well is not only the drill bits that we needed for high performance, but also the operation parameters you run these bits at, and these are required to have what we used to call drill off tests, but also minimizing all the things that's holding you back. One of them is really some automation on the rig that will hold the bit in a different position or drill off to be zero. And that's kind of what we're preaching here, not to do that. So it's a little bit of a change in mentality on how to approach the drilling of these hot rocks. This has been applied, and all these learnings are gonna turn to be a great thing. If you look at this as a forge well, we drilled the previous well that was drilled so many years ago. This 416 was drilled about 3 years ago, and you have the record run for it. Basically, it's 140 feet for the bit, which is again, when you talk about oil and gas, this is basically nothing. We're looking at 4,000 or 5,000 feet runs here. However, remember this is a very hard rock and very hard rock to drill. But they improved on that on the second run. We have on the second well. I'm sorry. We had a record run on the third one. We had 2,000 and over 100 feet an hour drilling that rock, which again achieved. And you can read all about it in this SPE paper here. But they have changed the drilling practices a little bit. We changed the weight on bit, the way we apply it. We have shape cutters. They perform drill off tests to find out what's the right parameter to do this. These are the two important things here in my mind. Workflow and training. Training for the people on the rig to how to deal with break information or kind of how to go back to bottom or how to start the bit on bottom, because that entails a lot more help in maintaining the bit life for longer. So PDMs is another important part as well. The normal PDM, of course, it has a lot of rubber lining here on the stator, on the rotor, and basically that is really kind of a deteriorate with temperature, to say the least, but it also cannot handle all that. Even if you have the higher component of rubber or elastomer in there, I think it's HNBR what they're using right now. But again, that's a maximum of 175 degrees Celsius that can handle that. And if we're looking at anything above the 200 degrees Celsius, then this is not applicable. It will chunk on you. So another approach was to use metal-to-metal motors. So metal motors, as you can see here, has no rubber components at all. So as such, have the capability of running longer without having any issues for the rubber deterioration. However, because of the close tolerance, you have to have very clean mud run through this. So it's expected to have top-of-the-line mud cleaners and all the solids control equipment in there to help you running a very clean mud to not affect all this tight tolerance for the PDM. So we have run the regular motors in IDTP2, which is the Iceland project in here. And basically you can see on the rotor have a lot of damage on the rotor here. And you can see it visibly by your hand, and you can refer to it as this SPE paper here as well. Drilling fluids is really the bloodline of any drilling operation, and you have to have a good drilling fluid to kind of counter a lot of the stuff we see in the drilling regularly in oil and gas. However, because of the geothermal system requirements and limitations, we basically running aqueous fluids, which is basically water with minimum bentonite and gels. There's a lot of researches going on to try to use new material, but the thermal stability of most of the additives and chemicals are less than required temperature of about 400 degrees Celsius. So we're still working with water-based mud. We still don't have any kind of solution for that for the time being. There's lots of circulation in some geothermal wells. It's frequent, as I said. And basically, we have the regular LCM material degrades with the high temperature. So we need to look at a good solution for that. So far, what we've been using is really drilling, having cement that zone, thick zone, and then move on afterwards. Which brings us to cement, and cement is also a very component, very important component in this equation here. Portland cement and silica flour traditionally used in high temperature wells for oil and gas. They cannot really work well in geothermal wells because we have a lot of heat recycling between the setting of the casing and the cementing, sort of the cementing and the water around it. And then basically it kind of deteriorate the cement and comes to a point where you cannot really use it for anything. It will be a kind of a isolation you're looking for, zonal isolation you're looking for. So typically what we have right now to add more retarders and friction reducers to offset the high temperature, or use a brand new type, calcium aluminate phosphate for thermal shock and resistant cement, TSRC. And these are still either a little commercial. We have some other types available, commercially used, but mostly is a lab testing from the national labs we have. Some techniques will help us place the cement really better and reduce the exposure of the cement to the heat. It's basically the reverse cementing. That's what usually reduces the time exposure for the cement for the high temperature. Again, we look at the cement and we look at the cementing accessories, and basically the cementing accessories have a lot of elastomers on them, and we have to be catering for that with a high temperature we're looking at, and we have to have a specialized FFKM kind of material in there to be able to withstand that kind of a temperature. MWD, we mentioned that the new EGS wells are going to be drilled with directional work. So this directional work is really important. And as such, you need to know where you are and as far as measurements for the well, direction, and or other things in there as well. Formation and chromation, vibration. But the MWD we currently have is basically 175 degree maximum Celsius. And some vendors look at having to changing things. So what they wanted to do is to do a kind of a enclosed or encapsulated MWD component and have a nice way to kind of a cool the well down, cool the tool down inside that encapsulated equipment, which called the viewer vessel. So they go through this factor here. When they start with a 300-degree, they control valve and reduces kind of a get evaporate and get a lot of zeolite kind of a system to cool the well, just like your AC. If you think about it, like your AC at home, kind of run a Furrion to really cool the weather around you. And this is basically what it is. It's kind of a reservoir impulse a little bit of things into the thermal flask, and then get the zeolite, cool down the electronic and maintain the 175 C temperature, which is the maximum for these electronics in there. And you can read all about it in this SPE paper here. However, unfortunately, this has not been used at all, and it's been shelved and I think discarded afterwards. So, in conclusions, what we're looking at here, what we need to do to drill into the 350 degrees C or more, that we need an AC rig with a mass capacity above 1,000,000 pounds to manage the heavy casing. We need high temperature BOPs, something we didn't talk about it, but all the elastomers in BOP is 300 Fahrenheit only, so 150 degrees Celsius. We need a corrosion resistant casing. Perhaps we don't need to go to the exotic material, not titanium and molybdenum, but we can use something else with modification. We need a high temperature drilling fluids. We need a high temperature MWD and LWD to help us into locating where we are and really explore this EGS system as much as we can. Low circulation is an issue, and cement is an issue, of course. So we need to sort all this to be able to get into really the geothermal kind of a performance that we're looking at from the oil and gas. And I would like again to thank GEODE and SPE for providing me the opportunity to do that. And this is the webinar. You can look at it and see what we have in there as far as the other webinars we have in the same system. And I would like to thank you all for giving me time to looking at this with you. Ahmed.
All right. Well, for the audience, this is the time for the Q&A. If you haven't already done so, please click the Q&A button. It's at the bottom of your screen and send in your questions. All right. So one of the questions I see, Hani, is why do geothermal wells require heavy rigs?
Okay, geothermal wells, depend on two things. Depend on the fluid, being run in and out of the casing. Such they require a bigger size casing, and a bigger size casing and heavier casing requires, if you go deeper, it basically requires a bigger mast to capture that. So if you look at the 958, 5350, for instance, drilling to about 15,000 feet, you need a rig capacity of 1.2 million pounds to be able to handle that. And yes, you can float it, but it's still heavy casing to handle.
Right. Well, I see another question here, and it's more about the lessons learned from oil and gas and how easily are they to transfer to geothermal wells?
Right. So, as I mentioned, there is similarities between the oil and gas approach and the geothermal wells, and as such, you can really kind of improve the well by recombination, having a little bit of open mind about having how to apply something into that. So, the idea of the shaped cutters, for instance, or the bits, is coming from having the better cutting incidence of the roller cones, which is kind of pointed, rather than having a really blunt one or circular. And that's why they improve the shape of the cutters. And you can see that improvement right now to apply higher Wickham bit as well. So it's easy to transfer.
All right. All right. So there is another question. It's talking about the wells that have been drilled, like, Iceland and Japan, and like temperature exceeding 500 degrees Celsius. And what's the difference in methodology versus, there versus what you're looking at?
Well, the wells drilled in Japan to about 500 degrees Celsius is really took about over 500 days to drill. So in looking at the cost versus value, you're trying to look into something equitable, right? So you cannot really use the same concept they have. This has been really long well to drill. Because the time it took them to run this MWD and pull it out after every run. And so that took a long time, of course. And then they burn a few MWDs, should I say. And that again, we're looking at, cost again. Same thing goes for the IDTP in Iceland. They really drilled the wells to deeper, depth, lower depth. But it's again, they cooled the well, but they kind of managed to lose a few things, as you can see from the design that they have somewhere around some of the PDMs they use and stuff like that. So very very good important kind of things. I think we missed talking about it here is how to cool the mud while drilling, and the use of mud coolers or chillers is a good thing, a good practice to have as well, and coated pipes as well. That's other things that we're looking at the moment.
All right. Well, thank you, Annie. Another question from the audience is the EGS wells tend to drill larger hole to casing about 9/7/8 a hole with a 7-inch casing. Is this due to dog legs being 5 to 10 degree on dog leg severity?
Right. So yes, the current practice from some of the operators right now is to drill 9/7/8. And again, the concept of drilling larger holes is there on the table. What they wanted to do, and I was in discussion with them yesterday, as a matter of fact, they're trying to go slim hole first to prove the concept, and then move up to a larger casing. But the idea is to really drill 12 and a quarter and have the 9/5/8 run in there on 10 3/4, as well as the dog leg severity because of the tool restrictions, if you like. They cannot run over a certain depth because of the heat. So they limit that to a vertical section and then go straight, and that creates the hard dog leg you see in there.
All right. Well, with that, I'll hand it over back to Haley.
Thank you for attending today's webinar and for all of your participation. Please use the QR code on your screen to complete a brief survey about today's presentation. Have a wonderful day.
Thank you.
Thanks,
Thank
everybody.
you.
Thank you.